Let's begin the video by introducing speed and velocity. Speed, or v, is a scalar value, whilst velocity, which we'll call v with our vector notation, is equal to vx in the x direction plus vy in the y direction plus vz in the z direction. In this example we're going to work in 1D, and therefore we are going to simplify v just to be vx x hat. And this is our velocity. The only difference is that speed can only ever be positive. It's a magnitude, whilst our displacement velocity, for example vx, which is the velocity in a certain direction, can be positive or negative, meaning it has a direction. For example, if a car is travelling at 10 meters per second, it's going the same speed whether it's going in front of you or whether it's going the opposite way, whilst for the velocity it could be plus or minus 10 meters per second. In this example, we're going to firstly draw a speed time diagram and then a x velocity time diagram. Let's start off by defining our axes. We have speed with the units meters per second, we have the origin, and we have t with the units of seconds. From our example you can see that our important times are going up in multiples of 5 until 30 seconds. So mark that on here. Firstly, we can see that the car accelerates from t equals 0 to t equals 5 seconds. This means that our velocity is going to be increasing as the car is accelerating from 0 until our time 5 seconds. As such. Secondly, the car stays at a constant speed until 10 seconds. This means that we will stay at the same height on our speed time diagram. There we are. After this, the car decelerates and comes to a stop at t equals 15 seconds. Therefore, we shall draw 15 seconds on here, and then our car is going to decelerate, which means the speed will decrease until there is no speed again. The car then stays stationary until t equals 20 seconds, and so therefore the speed is still 0. After this, the car reverses, in which it accelerates backwards until t equals 25 seconds before immediately braking or decelerating before coming to a halt at 30 seconds. As speed is the magnitude of its velocity, it means that even when accelerating backwards, the speed has still got an increasing magnitude, meaning at 20 seconds we will have our gradient heading back up. As such. This will be 25 seconds and this will be 30. At 25 seconds the car immediately starts braking again before eventually it will come to a stop at v equals 0 at t equals 30 seconds. Let's do the same thing for the x velocity time diagram. Let's draw on our origin, our x velocity with units meters per second, our time with units seconds, and we'll mark on our 5 to 30 second marks once again. The graph is going to look very similar to begin with. Once again, our car accelerates until 5 seconds, before staying at a constant velocity until 10 seconds, and then decelerating until 15 seconds. And let's mark the times on there. The car then stays stationary until 20 seconds, and this is the point we begin at again. Now, Our car reverses, which means it accelerates backwards until 25 seconds. But here is a slightly different part to the speed time diagram. Now we have directions to deal with, which means if our car accelerates backwards, it means that the x velocity will be increasing but in the opposite direction, meaning that now we draw on the other side of the graph as such. This is quite a steep acceleration, it seems. Then, after t equals 25 seconds until 30 seconds, this point here, the car will decelerate and brake until a velocity is 0 at 30 seconds, which means now the car is going to decelerate, and so the velocity is going to trend to 0 meters per second, meaning we can draw a line back to Vx equals 0. Before we finish up this section, let's talk about the properties of the graphs. Firstly, we can talk about the area. If I was to draw a square in one of these graphs, you would see if I wanted to find out the area of the graph, I would have to multiply the distance in the velocity axes by the length in the time axes. When we multiply a speed and a time, we get a distance, s. This was outlined in our previous videos. Therefore, the area on a speed time diagram is actually going to be the distance travelled, meaning if I calculated the area of everything I'm shading here, we could find out the total distance the car travelled. Secondly, we can talk about the gradient. If I was to draw a right-angled triangle and I wanted to find out the slope, then we would take the change in the velocity and divide it by the change in the time to get the rate of increase of speed with time. It turns out that this is actually the acceleration. We'll have a go at calculating some of these later on. It's very similar for a velocity time diagram, but this time the area will be the x displacement and the gradient will be the x acceleration. Notice that now when calculating the area, we'll have an area on top and an area on the bottom of the graph. In examples later you will see that we actually add the area on the top and subtract the area on the bottom, meaning that the total displacement of the car when moving forwards and then moving back will probably be quite close to 0 as we both add and subtract some area. This is very realistic. We can tell that the car has not moved very far in total. However, this graph here, the speed time diagram, would only show the total distance travelled, which means there is some information loss when going back to the speed time diagram. Let's move on to an animated example. Welcome to the simulated part of the tutorial. This is used so you can get a better idea of what a real-life speed or velocity time diagram might look like. This simulation, along with all of the A-level revision tutorials, is taking place on the exoplanet TRAPPIST-1d. This means it has a slightly different gravity to that of Earth. Let's draw the speed time diagram first. As you can see, the speed, which is shown by the vertical axes, increases. At first, at 0 seconds, we have 0 speed. This makes sense, as the wheel must start at 0 speed. There is a small spike, which is seen up here, that happens within the first quarter of a second. Therefore, this is actually when the wheel falls to the ground. As you can see, its speed then quickly lowers once it's hit the ground. After this, we see a steady increase in speed. If you remember, a gradient on a speed time diagram is an indication of an acceleration, meaning that we can see the wheel accelerates down the hill. When we get to approximately 2 seconds and beyond, the velocity levels out somewhat, therefore meaning it travels at a roughly constant speed. This is shown by a very shallow gradient or no gradient at all, indicating very little acceleration. After this, from 4 seconds and beyond, we start to have a downwards trend in speed, or a deceleration. This is actually when the wheel is travelling slightly up a hill, meaning that eventually its speed will slow. At the end, at roughly 9 seconds, you can see that the wheel comes to a stop, as the speed has decreased to approximately 0 meters per second. Let's now draw the x velocity time diagram. Keep in mind that the x direction is pointing almost exactly in the direction of motion. This can be seen on the video itself. As you can see, the two graphs are very similar. This means that we can tell that most of the motion is actually in the x direction, meaning that the y direction does not really contribute that much. These two graphs may seem slightly different, but actually they've got even more similarities than you might think. If you look at 6 seconds and onwards, you have a downward spike in the x velocity, whilst if you look at 6 seconds and onwards in the speed time diagram, you have a peak. If you remember me saying at the beginning of the tutorial that speed is a magnitude and therefore cannot be negative, if most of the movement is in the x direction, then we can actually say that the magnitude of the x velocity would create an upward spike like this. It would be mirrored along the Vx equals 0 line. This shows once again that most of the movement is in the x direction. It must be because the x velocity and the speed diagrams are almost identical. Any variations in the graph come from movement in the y direction or the z direction. Hopefully this shows how having a velocity graph could be much more beneficial than just a speed graph, because from one velocity graph, although we only have the information for one axis, we can determine that the other two axes don't have much movement in them purely because of its similarity to the speed time diagram. Let's do an example. Here we have a speed time diagram that has at first an increasing speed and then a decreasing speed. Firstly, we got to list the speeds at 2 and 4 seconds. We'll start with question 1. At 2 seconds, we can trace up the graph and we can see that our line corresponds to a speed of 4 meters per second. Very simple. And let's do 2 along the same line. We have to do the same for 4 seconds. And so we find 4 on the time axis, trace up, and we see once again that it corresponds to the value 4 for the speed. Therefore v, the speed, is once again 4 meters per second. For question 3, we had to find the acceleration at 2 seconds, and then for question 4, we had to find the acceleration at 4 seconds. We can see that the speed time diagram has the same slope between 0 and 3 seconds. Therefore, when finding the gradient, we're going to consider this time period as a whole. We know that on the speed time diagram, that a, the acceleration, is equal to the change in speed over the change in time, which equals the final speed minus the initial speed divided by the final time over the initial time. We are considering the period with the same gradient, which is 0 to 3 seconds. We can see our final speed is equal to 6 meters per second. This is at the final time of 3 seconds. And we can see that our initial speed at 0 seconds is 0. Then we know that our final time is 3 seconds and our initial time is 0. This gives us 6 divided by 3, which is equal to 2 meters per second squared. Let's do question 4. Once again, we know that the acceleration is equal to the final speed minus the initial speed over the final time minus the initial time. Now we're trying to find the acceleration at 4 seconds, which is this point on the graph. We can see that the graph behaves the same, or has the same gradient, between 3 and 6 seconds. So therefore this is going to be the time period that we consider, and we're going to ignore 0 to 3 seconds. Therefore our final time will be 6 seconds, and our initial time will be 3 seconds. Therefore our final speed, which is the speed at 6 seconds, is 0, and our initial speed is the speed at 3 seconds, which is 6 meters per second. And then our final time is 6 seconds, and our initial time is 3 seconds. This gives us minus 6 over 3, which is equal to minus 2 meters per second squared. This means we have a deceleration at 4 seconds. Let's move on to the last part, where we need to find the distance travelled at 3 seconds. You may remember from earlier on in the video that on a speed time diagram, the distance s is equal to v delta t, or the area. Therefore, if we want to find the distance travelled, which we shall draw a line down and do our working here, we will need to find the area between 0 and 3 seconds, which we can shade in as this area here. If we find this area, then we will find the distance travelled. So how are we going to find this area? Well, in this question it's rather easy, because we simply have a triangle. We're going to write that S is equal to the area, A, which is equal to 1/2 times the base of the triangle, which is 3 seconds, times the height of the triangle, which is 6 meters per second. This gives us 9 meters. Therefore, by the time 3 seconds has passed, our object has moved 9 meters. Let's move on to a velocity time graph. This is very similar to the other question, but now we're considering a vector quantity rather than a scalar quantity, and specifically in the z direction in this question. Firstly, we need to find the velocity at 2 and 4 seconds, which we will denote as Vz for the z velocity. This is just a matter of reading off the values. We see at t equals 2 seconds, if we trace up, we have a velocity of approximately 2.5 meters per second. For question 2, we need to read off the value at 4 seconds. We trace up at 4 seconds, and we see that it roughly corresponds to minus 2.5 meters per second. This is fairly simple. Question 3. For the next 2 questions, we need to find the acceleration. If you look, the entire graph has the same gradient, and we know that the acceleration as a vector is equal to the change in velocity over the change in time, which is equal to the gradient. If this entire graph has the same gradient, then it means this entire graph has the same acceleration, meaning that we only need to do one calculation. Therefore we will write and for. As a whole graph has the same gradient, then we can take the final time to be 6 seconds and the initial time to be 0 seconds, and we can use the entire triangle. Therefore, we shall write that A in the z direction is equal to the change in the z velocity over the change in time, which is equal to the final z velocity minus the initial z velocity over the final time minus the initial time. we're going to choose our final time to be 6 seconds, so therefore the final z velocity is going to be minus 9 meters per second. As you can see, it's nearly touching minus 10. And then our initial z velocity is going to be the velocity at t equals 0, which is 9 meters per second, almost touching 10, as such. Then our final time is 6 seconds, and our initial time is 0 seconds, giving us minus 18 over 6, which is equal to minus 3 meters per second squared for the z acceleration at both times 2 and 4 seconds. This means throughout this entire graph there is a deceleration or a decreasing acceleration, however you wish to say it, in the z direction, which makes sense because over time the z velocity is becoming more negative. Lastly, we need to answer the displacement change question. I'm going to denote displacement down here, just so we can corner it off from the rest of the work. We know from earlier that the displacement is equal to the velocity times the change in time, or the area, in other words. Therefore, we can say that the z displacement is equal to the area of the graph, A. We wish to find the displacement change by 6 seconds, which is the very end of the graph here. And remember that our 0 velocity line lies along here. When working out areas with negative values, everything above the 0 velocity line is a positive area, and anything below the 0 velocity line is a negative area. Therefore, we're going to split this question into two. We first must work out the positive area, and then add the negative area to it. Therefore, we're going to say that the total z displacement is going to equal area 1 plus area 2, where area 1 is before 3 seconds, then area 2 is after 3 seconds. Area 1 is a triangle, so we work out the half times the base times the height, where the base is 3 seconds. If you look at this triangle here, 1/2 times 3 times the height, which is 9. Now we add on the second area, which is once again 1/2 times the base times the height, where the base is this distance here, which is 6 minus 3, which is 3 seconds, and then the height. But now you see the height is going downwards, meaning that our height is now -9. And you should be able to see that these two will cancel each other out, meaning we get 0. Now this might be confusing. Why has our total z displacement came out as 0 meters? Well, think of it this way. Initially, we started with a positive z velocity, and so we're moving forward. Eventually we come to a stop, and then we start moving backwards in exactly the same way, meaning that by the end of the 6 seconds, we've moved forward and we've moved back to where we start, meaning that our displacement from the initial starting position is 0 meters, meaning we have not moved at all. This is why we have a 0 meter z displacement. Thank you for watching this video tutorial. Visit my website coherentphysics.com for many examples with fully worked solutions.